It's not done yet. Hey, Allison. Okay. Okay, so there is going to be some terms that remind you of calculus in your lovely classes. That's not what I'm focusing on, but those of you who take calculus next year, you'll be like, oh, we totally did this in chemistry. Okay, so this is just called a rate law. They are technically called differential rate laws because later on we're going to get to integrated rate laws, something called derivation. What's it called here? Derivative. Thank you. And intervals, which is those words are going to ring a bell to some people. But differential rate laws are just rate laws. That's what you'll be calculating today in some of your problem sets. But they compare concentration to rate. Those are the two variables you have to be given in a table or a graph, or you actually calculate in the lab yourself. Those have to be given to you. No time is included in differential rate laws. Time is only associated with the rate itself, because you know rate is concentration over time. So that's the only place time is really included. And we're going to talk about today how some reactants that are in a reaction control the rate more, so they're more important, like Crystal is. Yeah. So they're more important in determining the rate because they act differently, or they're more complex, or they have to kind of orient themselves in a different way. So there are some things that are more important in controlling rate than others. That's what we focus on them, or we say they're first or second or zero order. So we're going to talk about that. Okay, cool. Okay, so in this reaction, A plus B yields C. Our reactants they do have a 1 and a 1 for their coefficients. Their coefficients don't matter at all in the rate. Okay, that is something called molecularity, which we'll hit a little bit later, but well, the way we write a rate law is actually writing out this equation based on the reactants, not on the products, on the reactants. So rate laws, reactants, remember that. Rate laws equals your reactants, and that's it. So I took my A, I put it in a bracket. Bracket means what? Molarity or concentration. B, same thing, bracket, concentration. And they are both raised to a particular power, X and Y. X's and Y's are not coefficients. They must be experimentally determined. They have to be experimentally determined from a graph, a table, or data you collect. And I'm going to show you how to do that. And some of you guys saw how to do it on the reading pages 1 through 12. You'll see some of that table logic and ugly algebra method here. So I'm going to explain that a little bit better here. And also in the rate law is the rate constant. So we have to have some sort of value that's commonly in all of the rate laws, and that value is lowercase k, not big K, something else for later on, equilibrium. So make sure you do that lowercase k. And the rate law constant, if you're comparing equal orders, like you're comparing first order of the 3 different reactions, you can look at the rate law constant and you can determine who occurs faster or who is speedier. Okay, very technical term. But who's speedier based on the value, the size, the magnitude of that rate law constant. But the rate law constant is temperature dependent. So temperature dependent usually means hotter things move faster, so therefore probably increasing the temperature would increase the K. Good important note to write down, okay? Make sure you know it's temperature dependent. And then the orders, this probably is a duh, but the orders are going to be the exponents. So orders are going to, in this case, are X and Y, and they're in reference to whatever reactant they are labeled as. Okay? Thanks, Sonia. Anybody else? Okay. And then I just told you that they're not coefficients. All right, so why do we have to determine rate laws? You can look at a graph and determine how fast something is, but sometimes they're going to help us with knowing the details of how a reaction occurs, and how a reaction occurs means mechanism. So steps of a full reaction. And what was the most important step of a reaction? The rate determining step or the slow step, right? So specifically, rate laws tell us a whole lot about the slow step. And the slow step is called the rate determining step, so I'm going to call that RDS, rate determining step. Rate laws specifically tell us about those because they determine the rate. Well, and if you're setting rate equals K concentration of A to the X, concentration of B to the Y, and you're equaling it to the rate, well, that has to be describing the rate determining step because you're equaling it, you're summating it, or saying it's the same thing as the rate. So that's truly what we were talking about. So Krista's our celebrity today. Or Grace. We have a couple of them. Okay, so today we're focusing on the concentration and the rate, the differential rate laws. Tuesday, we're going to focus on the integrated rate laws, which is using time as a factor, as a variable. So those are the two types of rate laws we'll deal with. So if you're ever presented where something is just with concentration and rate, you are going to have information for a differential rate law. That looks different visually than an integrated rate law, which is a little bit of a longer formula. So that's why I put those variables up there, so you can kind of go ahead and start thinking about how are you going to look at some numbers in a table and say, okay, I need a differential rate law from this, or I can get an integrated rate law from this. Okay, so let's try one. Oh, this is on your packet. FYI. I copied these things and I forget to actually. Okie dokie. So I have a big, huge reaction. Looks kind of redoxy to me. But I'm already given the rate law. You guys find it? Is this on there? I don't know. Where is it?
Yeah, it's right up top.
Top right, thank you. It says differential rate law notes. Yep. Where is this? Someone left those in here yesterday.
Oh, can I give you some more? I stole this. I'm sorry.
Okay, so looking at this rate law given to me, what exponents are given to me for my reactants? What exponents? 1, 1, and 2. Okay, so the exponents are the orders. All right, guys, you can do this. What is the order of this? 1. Order of this? 1. Order of this? 2. Overall order? Yes. You add them up. So overall order of this full reaction is 4th order reaction. All right, so now what this order thing means is that tells you how the reactant itself affects the rate. So if this guy is first order, then whatever you do in terms of multiplying the concentration, that same thing, that same multiple is applied to the rate because it is first order. It is directly related. So if I do HCRO minus times 2, I take its concentration times 2, what's going to happen to the rate? Right, the rate will also times 2 or double. Make sure you're writing down a couple. Oh, well, I don't have that written. I'll write this down right here. So if I do the same, let's say I take the H plus concentration and I multiply it by 3, what's going to happen to the rate? It will also triple. So these are directly related. And I'll tell you why. Because these concentrations, they have an exponent applied to them, right? What is the exponent for this one? 1. So 2 to the first power is just 2. So that's why this is 2. 3 to the first power, because this was also first order here, is 3. All right, let's do this one. Concentration, let's multiply it by 2 here. What is the order of this one? 2, so the exponent is 2, right? So 2 to the second power, 4. So the rate should then quadruple. That's a multiplication right there. Okay, so it should quadruple. So you have to think about concentration, raised to that exponent, and then do that same thing to the rate. If something were third order and we doubled it, it would be like going, okay, so A times 3, not 3, we're doubling it. A doubled is times 2. Got it? Okay. And then this third order, so it has an exponent of 3. My rate will be multiplied by 8, not 9. Okay? 2 times 2 is 4 times 2 again, 8. People always say 9. I'm like, no, you're multiplying. You're not doing the exponents here. All right, so that's not bad, right? We can do first order. We can do second order. You just have to think about how the concentrations are changing. These are the different types of rate laws you would see for the different orders. Write down what you need to. If you know first order has rate equals K and A, or A is just my generic reactant to the first power, you're good. A to the 0 power means it's 0 order or 0th order, but commonly the A to the 0 is reduced down to 1 because anything to the 0 power is 1. So usually it's just written as this. And you can recognize this rate is equal to K, which was that rate law constant, because earlier we had our little 0 order graph. I'm doing versus time right here, but my 0 order graph went down. The slope was representing the K, the rate law constant in that case. So that's one we've already kind of encountered. The last two, or last one, is a summative nature here. You got overall order 3, the overall third order. So you say it in this particular way. It's second order with respect to A. It's first order with respect to B. Overall third order. So the lingo is just a teeny bit different here.
Could you have just like A to the third, would that be the second one?
A to the third would be overall third order. Yeah. All right, I have one more thing with units and we're going to do some problems. This is a very practice-based knowledge. You have to practice it to really learn it. Me just talking let me tell you all this information is not really that helpful. Okay, so let's talk about the units here based on our knowledge of what the rate laws look like. So first blurb to know, for any particular reaction, the K is constant. The K, the rate law, the constant. Because it's a constant. That's why it's constant. Does that make sense? It is a constant. So it is a constant because it is a constant. Or it is constant because it is a constant. You picked up what I'm putting down. It determines, if you're comparing different things, you can determine if something's happening faster. But there's other background details that control the K value. Things like surface area, ionic strength, if you're dealing with something ionically bound because they have a strong attraction for one another. Temperature, definitely. It's the most important. Because I told you earlier, it's temperature dependent. That's an easy question you would miss. They've had on the AP exam the past 5 years, random thing today. But the units of K are going to be different on different rate laws because it has to fit the units of the overall rate law. So the rate always has the units it has to have. Rate always has units of concentration over time, always. So in my example here, rate is equal to K times concentration. You know, rate is molarity per second. You have to tell me what K's units are in order to get the appropriate units, because concentration is just molarity. So what does question mark have to be? 1 over second, because this is per second, right? So question mark has to be per second, also written as second to the -1. Okay, so that's something that you need to be very comfortable with. So that is a what order reaction? First, because that's A's to the 1. So that's going to qualify here. Yeah, I was that's not right. That is right. Okay, so let's do one for rate is equal to K. So what order reaction is this? 0. So if rate is molarity per second, what is K? Molarity per second. Or molarity times second to the -1. Commonly written that way. Or, wait, there's more. Molarity, moles times liters to the -1 times seconds to the -1. Where they take molarity and they break it into the 2 units and they pull that liter that's on the bottom to the numerator. So you have to say, oh, it's not in the numerator, it's actually in the denominator. You put a -1 there. Okay? These units are very important. You must write your units for this. So there is our 0 order one. So let's do the same thing, but for which one? Second order. So K, A to the squared, to the second. We'll do this one right here. Okay, so rate is molarity per second. K, I don't know. A, I do know. It's molarity squared. Okay. Notice that I have molarity squared on the right, only just molarity up there. So what has to be in the denominator of K? Molarity. 1 molarity, right? Because I have to be able to cancel out one of those molarities to yield only 1 molarity in the numerator. So K has to be, I'm just going to put 1 for now. 1 over molarity, but what else is it's going to occur in the denominator? Seconds. So that's it. Those are the units for K in the second order ones. Now, I don't recommend you memorize that because that's like dumb space that you're just taking up in your brain, because you can do that. Like we just did this here. Don't memorize these. Work them out. Write your units. Cancel them out. Think about what has to be in the numerator, what's in the denominator. Don't waste your brain space. You got bigger problems. Okay? There you go. Oh, also written as liters, because, you know, molarity on the bottom, if it was 1 over molarity times seconds, molarity in the bottom is technically 1 over moles over liters times seconds. But those liters go floppy top up there. That's liters over moles seconds. And that's why you get the moles in the bottom with the liters on the top. Good? We're going to practice that, okay? So here we go. I'm going to explain one or two, and then we'll do some together. So rate laws are experimentally determined. So it's going to say an experiment was occurred with blah, 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 and then here's some information from it. Data. So they give us a reaction. I could care less about the reaction because the coefficients don't matter a whole lot. The only thing I care about is I know rate, the general rate law looks like rate equals K, A to the I don't know, and then B to the I don't know. Okay? So X and Y's work for me, or question marks, whatever. Your job is to figure out those orders. The way you do it is just by comparing. This is a table logic method. This is the one that was in the first example in your exercises. So looking at the different trials, you can see that we collected information for concentration of A, concentration of B, and then the rate of the formation or the rate of the reaction. The way you do it is you choose one reactant to remain constant, so it's a controlled experiment, you only change one variable at a time. One reactant stays constant, one of them changes, and then that influences the rate. Maybe it does, maybe it doesn't. We have to figure that out. So I chose to go with, I'm going to go with A first. Concentration of A from trials 3 to 4 remains constant. This is how I do it. I just draw a straight line to say that's constant. Comparatively, B does what? Doubles. Okay, so the concentration of B is doubling. How does that affect the rate? It quadruples. Okay, so 2, so you're taking concentration times 2 to the what power equals 4. 2. See how we do that table logic? You're just doing the math in your head. Okay, so I always, because I'm scared I'm going to forget it, I know that the question mark here, the order is second order, so right at the top of the table so you don't forget what you just, worked so hard to get. All right, so that's second order, so second little o means second order. All right, so now I have to consider different trials because I got to find the other one. I have to say, all right, B has to stay constant this time while A is changing. So the two trials where that occurs is trial 1 and 2, where B is staying constant, A is doubling, and the rate is also doubling. So that one's a direct relationship. But just to keep your math, right here at the top of your brain here, 2 to the x power equals 2. So what is x? X is equal to 1, so that's first order. Thumbs up if that makes sense. Yes. Okay, good. So we now know the orders, right? So I can write this rate law in the correct way. K, A to the first, concentration of B to the second. Do put your brackets. They don't give you they don't even give you credit if you put parentheses, because parentheses don't mean crap. Brackets mean molarity. That's a common symbol for that. Okay, now we also determined the rate law check. We need to determine the K constant, the rate law constant. And then I was going to show you another way to sub into this. So for the rate law constant, we know a rate, we know the concentrations, and we know the orders. The only thing we don't know is K. The way you do it is you plug in I usually just take the first trial, and I'll plug in all the information from trial 1, because I have the rate, I can find K. So let's do that. Guys, you have to tell me the numbers because I'm going to scroll down. So rate is equal to K, A to the first, B to the second. I'm going to isolate K and then plug in numbers because I just like to do that. So K is equal to what? Rate over A to the first, B to the second. All right, give me the rate for trial 1. 0.20. What? Molarity per second. I do that all the time. Okay, molarity per second, and then the concentration of the A and B. 0.1 molar to the first, and then 0.10 molar to the second. Okay, so what's this on the bottom? 0.1 times 0.1. 0.01. You move decimal over once. Times 0.1 again.
0.001.
Right, there you go. So 0.020 molar per second over 0.001. These two things multiply by each other. What units? Molarity cubed, because molarity to the first times molarity to the second as you add your exponent, so molarity cubed. Okay? 20 divided by 1? What is that? I think it's 200, isn't it?
Yeah.
0.02, move the decimal over one more, 200. Okay, so that's the number. What are the units, though? Alright, I'm going to write your units as two individual fractions, just to be clear on the first one, and then I'm not going to be babying you. Yes, so this is molarity per second, and then this was molarity cubed over 1. So then these go together, and then these go together, right?
Thank you.
And so this is 200. The big M and this one go on the very top one and the very bottom one go together on the numerator, and then these go together in the denominator. So that's molarity cubed times seconds. So then what cancels? One of these. So that's down to 2, right?
Yeah.
So then you're 200. I don't know the sig things. I'll have to go back and look. 1 over m squared seconds. We're going to get real picky here. Yeah. I copied it from the table. The rate was 0.2 for trial 1. The value of rate?
Yeah, when you wrote out your apartment too.
Oh, that's why I couldn't math my head right. Okay. I'm sorry. Did that on purpose. Okay, there you go. Sorry. Ignore that. Thanks, guys. Here we go. We're good? Okay, so we can calculate K. This is K. But normally the question will say, what is the value of K with proper units? Because if you don't get the units right, you don't get the points, period. No halvesies. So that's why it's very important to write the units for everything. Let's do another one. Okay, so you guys tell me process here. I want to do ugly algebra. Let me do ugly algebra. Because that was table logic. Yeah, I'll do ugly algebra with you. This is what I want to do with you. So I'm ignoring the reactants because the coefficients don't mean anything. My ones that stay constant, I can easily see B stays constant from trial 1 to 2. What happens here? Doubles. So 2 to some exponent is going to cause this to happen. Okay, so nothing changed. So no change means that concentration of A changing doesn't do squat. So it is not involved in the rate law. So it's got a 0 order of its ordered. Okay, so notice that we can't do table logic for the second one because A doesn't stay. Oh no, it does. Okay, let's try that, and then I'll show you the ugly algebra. A stays constant from here to here. So trials 1 to 3. What happens when between B for trials 1 to 3? It doubles, and then from trials 1 to 3 for rate. 7 times 7. 7 times 4 is 28. So 7 times 4 is 28. Exponent moved over. You can see it. Just be one with the board. Okay, so this is times 4. So 2 to the x equals 4. So what's x?
600.
Right. And I'm just doing this baby step because I want to make sure we're all on the same page. So that's second order. So we have the rate to be k, a to the 0, b to the 2. Sometimes you can write that, just say, look, I actually know the 0, I didn't forget the a, it's actually 0, just to kind of put it out there, or if you don't write it, you'll get still get your points. Let's determine the K value. Sorry, I was like, where's my questions? Let's determine the K. Which trial do you want to use? Can we use the first trial? Is that okay? Okay. So rate of the first trial is 7.0 times 10 to the negative fifth molarity per second, about 10 meters. K, and then A doesn't matter, so I'm not going to include it. B does matter, because if I put A in there to the 0 power, it's just going to be 1, so that's why I'm ignoring it. B is 0.1 molar squared. So K is going to be, I'll work out this part, 7.0 times 10 to the negative fifth molarity per second over 0.1 times 0.1, 0.01 molarity squared, right? Because this is squared here. And then, so what cancels on our units here? So one of them, so what are the units of K? One of these ends cancel, right? Is seconds actually in the numerator, though? No, it's in the denominator because it's per seconds. So that's still going to be 1 over m is in the bottom, and seconds are in the bottom. Molar seconds. All right, and that value is 7 something. I know 0.07 because this is 10. This is 1 times 10 to negative 2, so negative 5, negative 2, negative 3. So 7 times 10 to negative 3. 2 sig figs, yeah. Okay. I don't know where my ugly algebra line is. I'll figure it out. It may have been on a problem set, and that's what I was going to do. Something with you guys today. Okay. Ready, Freddies? Let's keep going. All right, so this one's a little different. We're going to write the rate law from the information given, which are super easy. The value of the rate law of the first order with respect to H and the second order with respect to NO. Write the rate law. Please go ahead and write this. Rate equals what? K times H to the 1, and O to the 2. Okay, that should be no problem. Calculate the rate. So we're calculating rate this time. With the initial concentrations of these to be blah and blah. What do you want to do? Plug them in. Okay, rate is equal to and I'm going to write this as it is should be written. Molarity squared on the bottom times seconds. H2 is 0.050 molar to the first, and NO is 0.010 molar to the second. That is one you can put in your calculator if you want to for that. I will go ahead and tell you the answer. The answer, because I know you can work your calculator, is 1.5 times 10 to the 8th. Automatically, you should know the units. I don't even have to cancel anything. Meters per, molarity per second, because it's just what rate is, not meters. Molarity per second. Because rate is just change in concentration over change in time. Okay, so know that, knowing the rate, to the negative 8, sorry. I'm trying to squeeze it on the board. Okay. So 1.5 times 10 to the negative 8 molarity per second. So knowing that, don't calculate. What's going to happen what will happen to the rate when NO is doubled? It's going to what? Because it is second order. So when this is quadrupled, when that is doubled and H2 is unchanged, then it should quadruple. So it should be what? 15 times 4? 60. 6.0 times 10 to the negative 8. It is still negative 8. Yeah. Molarity per second. So you don't even have to recalculate. You just have to think about how the rates are related. Okay, almost done. I think I got one more with another example. What is this one? Let's look at this one. Oh, this one just has a review from yesterday. Okay. So using information, notice that the rates are given to us as appearance of NOBR. Okay, that's gonna be important later on. So determine the rate law. Tell me how you do it. Okay, so go ahead and tell me. 1 and 2 is constant. What's happening here? They're doubled. So stick. Yeah. Once you run the constant, go find the ones changing and then go on. What's happening here? Okay, so that's doubled. So what is this X here? 1. Right, so this is first order. So bromine, first order. What? I don't know what happened right now. I got too many things going on. All right, let's go ahead and do another one too. So what's happening? Which 2 trials do you want to use for the next order determination?
1 and 3.
We can do 3 and 4. We can, but we don't know the rate here, so I can't use 4 because I can't compare something to an unknown. Okay, so 1 and 3. So from here to here, you're constant. From here to here, you're doubling. And from here to here, you are quadrupling. So this is to the second, so that's second order. Okay. And do you want to go through this whole thing? Yeah, I have to. Okay, so let's write down the orders. Rate is equal to K, what was that first one? NO to the second, and then BR to the first. All right, I'll determine the rate law constant here for you. Plug. Calculate. K is equal to 1.08 times 10 to the second molarity per second. So what's molarity squared? Oh, no, I just determined the rate. I'm sorry. That's not the K value. That's a rate for the next problem. Okay, so K is 1.2 times 10 to the 4th per meter squared seconds. I was like, pretty sure I knew meter squared there because knowing that this is molarity squared and that's molarity first, that's molarity cubed. How do you get back to molarity? Just single molarity, the K has to have a molarity squared on the bottom. So you can, once you get really good at the units, you can continue with that. All right, so K, we're good. Rate of appearance for NO in trial 4, all you would be doing is plugging in the values of the concentrations with your K value to find the unknown right here. Okay, good with that? How you would do that? Yep. So all you would do is plug in, I have to get this smaller here. You would be, to find the rate of appearance for NOBR in trial 4, you'd be plugging into your rate law the value of NO and the value of BR and your rate law constant. So you'd be doing K, which was 1.2 times 10 to the 4th, divided by meters squared seconds, times concentration of A, which was what? 0.30 molar squared, right? Or NO, sorry, A. And then this one is 0.10 molar to the first. Plug, equals, that's the one I just wrote down. 108 times 10 to the second, so 108. Yes, ma'am.
The first line in the chart.
Usually, to determine the K value? Usually, yeah. It should be really, really close on all accounts, and any trial you use, it should be the same. Sometimes it varies a little bit depending on the data given, but it should be really close. So that's 108 molarity per second. And then last question is what I really just want to get to. What is the rate of disappearance of BR2 when this is this and this is this? So just tell me how you would do it. Notice that the rate is in reference to something else, not the rate of formation. Yeah. Right. Okay. So you're using mole ratios, essentially, because you have a coefficient given to you, 2 NOs and 1 BR. So if, and this is relating back to our relative rates, this is going to be forming twice as fast as BR disappears. So to determine the rate of disappearance of something, you would half it. So whatever you get by plugging in these values into the rate law, the rate that you get, whatever that number is in formation of NOBR. And so you put that number here, I guess, and then you would say, okay, well, I use 1 mole of BR2 for every 2 moles of NOBR made. So essentially you're halving it, but I rate it as mole ratios. That's the only weird question on there.
Would you just have the number?
Yeah. Yeah, so like whatever your number that you get, the number that you get here, just FYI, is 12.5 molar per second for the appearance. So that's 12.5 molar per second. Then the disappearance of Vr2 would be what? 6.25 molar per second. And that's just you halving it. I just show my word for it. Okay. Let's do some problem sets. Yeah, we're doing good. So like 135 right now? Yes, okay. So start with the one that's called differential rate law problem set. And then I'll give you guys I'll give you some time on that. I want to do one complex with you because that's the algebra way. So start on your problem set, use your time wisely. The more time you use now, the less time you will use them. Do you see where they are in your packet?
It's supposed to be.
Okay, it's differential rate law problem set, and then the next one says using initial concentrations to determine the orders of reaction complex. So that's what you're doing after that. Work by yourself for a little bit, and then work with a partner so that you can get some answers. Yeah, Crystal.